Okay, hi everybody. So in this video, we will continue our work with orthogonal sets, and we'll see some additional reasons why finding an orthogonal basis for some vector space or subspace is going to be particularly nice. So let's first define what we mean by an orthogonal basis, An orthogonal basis for some subspace W of Rn is a basis for that subspace W that is also an orthogonal set. So an orthogonal basis satisfies two things. All of the vectors inside of it are orthogonal to each other. And secondly, that set is a basis for whatever the vector space or subspace that we're studying. So let's take a look at a couple of examples and non-examples. So for example, if I take set S1, which consists of three vectors from R3, the first one, 1, minus 1, 0. The second one, 1, 1, 0. And the third one, 0, 0, 1. Well, we have shown earlier that all of these vectors are orthogonal to the other vectors in the set. So this set is an orthogonal set. So they're linearly independent. So if I have a set of three linearly independent vectors from a three-dimensional space, R3, it has to be a basis for that space. So this set S1 is an orthogonal set that is also a basis for the entire vector space R3. Down below this second example, S2, that consists of three vectors from R3 again, but now we're going to change the first vector in this set to 1, minus 1, 1. And the second vector we keep the same, 1, 1, 0. And the third vector in this set we keep the same as the previous case. It is 0, 0, 1. So this set, these three vectors are linearly independent, and there's three of them. So we've shown that if I have three linearly independent vectors from a vector space which is three-dimensional, then this set has to be a basis, but this set is not an orthogonal set. So namely, if I take the dot product of this first vector with this last vector, we get 0 plus 0 plus 1. So we get something which is non-zero. So the first vector is orthogonal to the second one. The second vector is orthogonal to the third one, but V1 is not orthogonal to V3. So that means this set is not an orthogonal set. So it is a basis, it's just not an orthogonal basis. Okay, so let's take a look at why an orthogonal basis might be a particularly nice basis to choose for a vector space or some subspace of a vector space. So let's consider some subspace W of Rn, and let's let B, which consists of the vectors u1, u2, up to up. We're going to assume that this basis B is an orthogonal basis for this subspace W. And now let's take some arbitrary vector, y will denote it, in this subspace W, and let's find B coordinates for this vector y. So recall that what the B coordinates of y would be what are the weights that we can use to combine the vectors u1, u2, up to up in our basis in order to get the vector y back. So we want to find values for C1, C2, up to Cp that are going to give us these B coordinates for y. So taking this initial equation, I'm going to perform the same operation to both sides. I'm going to take the left side y and take its inner product with u1. And I'm going to take the right side and also take its inner product with u1. So that's going to result in a new equation down below that says y dotted with u1. That should equal c1 u1 plus c2 u2 all the way up to cp up dotted with u1. And now let's go ahead and simplify the right side of this equation. This is going to be c1 times u1 dotted with u1 plus c2 times u2 dotted with u1 all the way up to cp times up dotted with u1. And again, we have assumed that B is an orthogonal basis. So we know that all of these dot products of u1 with anything other than u1 is going to be 0. So I'm going to get 0 plus 0 plus 0. All of these other terms are equal to 0. So the only thing that will be left on the right side of this equation is this first term, c1 times u1 dotted with u1. And so now we've got an equation, and we can solve this equation for c1 to identify what the first weight would be, what the first coordinate would be for y. So namely, I can divide both sides by u1 dotted with u1. So now we've got this nice result that given any vector y in this subspace W, we can find the first b coordinate c1 by taking y inner product with u1 and divide that by u1 inner product with itself. And we could repeat this process by picking u2 to take the dot product on both sides, and u3 and u4 and so on. And we can get a general formula for the Cj weight by taking y inner product with uj and dividing that by uj inner product with itself. So this is a really nice theorem that we can summarize on the right, which is namely, if S is a set of p vectors u1, u2 up to up that we know is an orthogonal basis for the subspace W, then for any vector y in subspace W, we can find the weights in the linear combination of vectors from our set S that will give us vector y. When we choose these weights, we can find each of these weights by using this formula that the jth weight, c sub j, is equal to y inner product with uj divided by uj inner product with uj. So this gives us a really nice way of finding b coordinates. When we choose b to be an orthogonal basis, this process gets simplified quite a bit, and we have a nice shortcut to apply. Okay, so let's see how we can apply that previous theorem to a concrete example. So let's consider an orthogonal basis for all of R3, which is given by this set below. So we're going to say that our basis consists of 3 column vectors from R3. The first one is 1, minus 1, 0. The second one is 1, 1, 0. And the third one is 0, 0, 1. And we've already shown that this is an orthogonal set, and therefore these vectors are linearly independent. So therefore these 3 linearly independent vectors do indeed form a basis for the 3-dimensional vector space R3. So we would like to find coordinates, say, for some vector y, which in this case is the vector 3, 7, 4. So in other words, what we would like to do is figure out what are the weights, we have 3 of them, that we would need to take a linear combination of each of these 3 vectors from our set and wind up with the vector 3, 7, 4. So there's going to be 3 numbers that we need to identify. And that previous theorem says we can find C1 by taking y inner product with u1 and dividing that by u1 inner product with u1. So that calculation I've computed over here. And you can verify that taking the dot product of y with u1 would be 3 minus 7 plus 0. So that 3 minus 7 comes from that inner product. And then the inner product of u1 with u1 would be 1 plus 1. And that's where the 2 comes from. So for C1, we get a minus 4 divided by 2. That gives us minus 2. And we can similarly find the other weights using the same sort of result. So for C2, I'm going to take y inner product with u2 and then divide that by u2 inner product with u2. And you can check that gives us a result of 5. So this tells me that the second weight is 5. And then to find the weight C3, we would take y inner product with u3 and divide that by u3 inner product with itself. And checking these dot products, you can verify that we'll get 4. So that gives me the third weight is equal to 4. And this gives us the coordinates of y relative to this basis, we can call this basis b. Then what we've shown is that y with respect to this basis b is equal to minus 2, 5, and 4. Okay, pulling off those weights. So you can check this arithmetic that minus 2 times u1 plus 5 times u2 plus 4 times u3 does indeed give us the vector 3, 7, 4 back.